Initially, I will request the Dr. Muhammad Jamil, supervisor student, to briefly introduce the student and highlights of his work. Then the student will present his presentation. During the presentation, examiners, they can ask the question, but other participants can ask the question at the end of the presentation. Once there are no questions by the participants, then only the exam committee will conduct the further examination for the final result of the examination. So I would request Dr. Muhammad Jameel to please introduce his student with his important research highlights.
Thank you, sir. Thank you. Please, audience, from respected chairman, it is requested that the audience will ask question at the end, and after then they are allowed at the end. So please, thank you. Bismillah ar-Rahman ar-Rahim. I am Muhammad Jamil, supervisor of Zahid Mir. I welcome to respected external examiners and audience for the defense of PhD by Zahid Mir. Zahid Mir is serving assistant professor at Superior University. He worked hard and published high impact in international reputed journals, a good number of publications, and inshallah, I hope he will successfully defend his research work. So Zahid Mir, you are common, please join.
Sir, is presentation is visible to you, sir?
Yes, yes. Please start.
Thank you, sir. Bismillahirrahmanirrahim. Rabbi shrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Honorable Chairman, respected examiner, and my kind teachers. Today, I am going to present my research work on the study of nonlinear interactions in dense plasma that I have done under the kind supervision of Dr. Muhammad Jamil and the able guidance of my co-supervisor, Professor Dr. Muhammad Asif. The sequence of the presentation will be as follows. First of all, I will explain the objective of our research. Then I will explain few of the terminologies that we have employed during our work. And then I talk about how nonlinearity is generated in plasma and its different types. Then I focus on the mechanism behind nonlinear resonant interaction. And lastly, I present two of my research works that are part of my thesis too. It was aimed to study nonlinear interaction that results due to the linear coupling of modes in dense plasma. To achieve this, we have done the theoretical work by employing quantum hydrodynamic model, and the growth rate of the beat wave due to parametric instability is derived. We have verified our numerical results through graphical plot, and the dependence of the growth rate on various parameters of the system was analyzed. Plasma can broadly be treated as classical or quantum, also known as dense plasma. A classical plasma is attributed with low number density and high temperatures, due to which there are fewer number of particles in the device sphere and experience thermal pressures. On the other hand, a dense plasma exists at high number density and extremely low temperatures. Now, there are large number of particles in the device sphere, and the thermal pressure is replaced by the Fermi degenerate pressure. And several quantum mechanical effects come into play that drastically alters the overall macroscopic behavior of the medium and show a significant effect on the propagation of various modes in the medium. Let me explain this difference through an analogy. In the picture you see, in the slide you see a picture. On the left side, there are butterflies which are separated from one another. So here we can presume that the insect part of the butterfly as the charged particle. This insect part represents the charged particle, and the wings represents the de Broglie wavelength associated with the particle. So here we perceive that this is the situation where these de Broglie wavelengths are not interacting, and hence we can ignore the quantum effects. On the other hand, the other picture you see, there are large number of butterflies whose wings are overlapping to each other. such a situation may arise when we enclosed large number of butterflies in a very small container. So here we presume that the de Broglie wavelengths associated with the charged particles are overlapping and hence interacting with each other. So this is the scenario where we cannot ignore the quantum mechanical effects. So a dense plasma exists whenever the interparticle distance is comparable or lesser than the de Broglie wavelength associated with the particle. There are a number of quantum effects that come into play once the plasma is treated as dense. I have incorporated three of them in our mathematical model. The first one is the Fermi degenerate pressure, which is a statistical pressure experienced by charged particles at high number densities. Classically, for non-degenerate gas, we know that there are many states available for the electrons to occupy according to their thermal motion. But for a degenerate gas, all the electrons are forced to occupy the lowest possible states up to a topmost field level, which is known as the Fermi level. The degenerate gas resists further compression because the electron cannot move to the already filled state. So it seems that certain kind of pressure is exerted by the degenerate matter, and that pressure is known as the Fermi degenerate pressure. The second term that we have incorporated is the bomb potential term, which represents the well-known quantum tunneling of particles through a potential barrier. Classically, we know that if a particle encounters a potential barrier and the energy of the particle is lesser than the energy of the barrier, then it cannot overcome it unless some external force is applied on that particle and to climb this energy hill. But if that particle is treated as a quantum particle, then it can tunnel through the barrier without crossing it. So this term represents the pure quantum mechanical in nature, and it represents the wave nature of the particle. The third term that we have incorporated in it is the exchange correlation potential, which represents a force that exists between identical particles due to their spin orientations. We know that two electrons can occupy a same quantum state if they have opposite spin. So if the spin of one of the electron is changed, then other electron will automatically flip its spin state too. So it seems that certain kind of potential is existed between the identical particles. So this potential is known as the exchange potential, and when this phenomena is observed along the dynamics of the system, then it is known as the correlated.
So you mean one exclusion principle to preserve
Pauli, sir? Yes, sir. The Pauli exclusion principle is preserved here. This is known as the Pauli repulsion, basically.
So what about the spin effect? In quantum plasma, the spin effect is also important, but why you are ignoring?
So there are many effects that we can include, like Bohr magneton, the quantization and magnetic quantization, etc. But we have incorporated only these three. We can include them, but we have focused only on these three. As I earlier said, there are many quantum mechanical effects that come into play.
So you are interested
only in these three. That's why I am explaining here. In our research work, we have focused on two kinds of dense plasma environments. The first one is the astrophysical plasma, which is regarded as dense due to high number densities and extremely low temperatures. White dwarfs, neutron stars, magnetars are few examples of the dense astrophysical plasma. On the other hand, the other medium that we have chosen is the semiconductor dense plasma. First of all, semiconductor is regarded as plasma due to its high dielectric constant. And secondly, it is regarded as dense due to the most of the case, relatively lower effective masses of the charge carriers. Semiconducting nano-electronic devices. Plasma hosts wide range of waves and instabilities, which shows various linear and non-linear effects in the medium. Once we are dealing with the waves of small amplitudes, then we are in the linear regime. And linear theory can be applied to explain these effects. Linear theory is based on the process of linearization in which the higher order terms of the dependent variables and their derivatives can be ignored due to their negligible contributions. On the other hand, if we are focusing on the waves of large amplitudes, then we are in the nonlinear regime. Or if the wave gets unstable, then even in the linear regime, it quickly gets into nonlinearity because the predicted growth rate is now exponential. Let me explain this difference through another analogy. In the slide, you see three pictures. The leftmost picture represents the surface of sea, which is very calm, and very small amplitude waves are propagating on it. In the middle picture, we see the waves of relatively large amplitudes, which may result into third kind of wave, which is the third kind of tsunami wave, which is basically the coupling of various waves. So, if you look at the amount of water in this turbulent wave, it is much lesser as compared to the overall water in the sea, but it has defining effect once it hits the shore. That's why nonlinear effects are so important to study. In plasma, there are nonlinear effects or nonlinear interactions can be categorized in two branches. The first one is the nonlinear effects that are observed is the steepening effects in waves, which are observed whenever the wave speed is determined from its amplitude. It leads to stationary solutions like shocks and solitons in the dispersive medium. There are several techniques to handle such kind of nonlinearity. A few commonly employed techniques are listed here. The first one is the nonlinear Schrodinger equation approach, which is a perturbative approach, and it describes the nonlinearity in a modulated wave packet when we deal with the waves of slowly varying amplitude modulations. The second one is the KDV theory approach. It is a reductive perturbative approach, and it is used to describe the nonlinearity in waves of large wavelengths. The kind of nonlinear effects that were observed is the nonlinear resonant interactions. And we have focused in this kind of nonlinear effects in our thesis. Nonlinear resonant interaction can be further categorized into the first one is the wave-wave interaction, in which a number of waves couples together by keeping the conservation of momentum and energy between them. These two conditions are known as the phase matching conditions, and they produce nonlinearity, and it is responsible for the transportation of energy to various regions of K-space. The other kind of nonlinear resonant interaction is the wave-particle interaction, in which two waves may couple together to produce a beat wave, and that beat wave is in resonance with the particle velocities, and it causes the waves to damp. Now,
particle और wave के दरमियान resonance होती है।
जी सर, पार्टिकल वेलोसिटी और वेव की फेज वेलोसिटी और ग्रुप वेलोसिटी के दरमियान
ऊपर wave और wave में
वहां पर सर वेव्स के दरमियान आपस में रेजोनेंस
किस चीज कौन सा फिजिकल पैरामीटर जिसको रेजोनेंस करेगा wave में एम्पलीट्यूड रेजोनेट करेगा जैसे कि आप कह रहे हो ना wave और पार्टिकल वेलोसिटी है उसमें wave और wave में कौन सी चीजें रेजोनेट करेंगी
सर यहाँ पर हम जो वेव्स हैं उनकी फील्ड्स आपस में रेजोनेट करते हैं और उनकी जो मोमेंटम और एनर्जी होती है वो आपस में कंजर्व हो रही होती है
सर ये बात है this wave interaction
सर
you study
beat waves
and in wave particle interaction
sir another beat wave is generated, but now the beat wave velocity or the phase velocity of that beat wave is in resonance with the particles velocities. So what happens that energy is transported from the waves towards the particle, which makes the wave to damp.
And you have studied, you are interested only in wave.
I have I'm not done any work on this. we have focused on wave-wave interaction in our work. This is also there. This is also there.
ये जो आप कह रहे हो beat wave beat, what do you think? Beat wave or the particle?
So beat
आप
wave.
sound में पढ़ते हैं FSC metric level में beats and sound wave.
Sir.
Quantum mechanically, what do you mean by जो उसको हम क्या कहते हैं?
So beat wave is the
quantum mechanical जो beat होगी ना, that's acts like a particle because it is the superposition of
many waves.
और वो जो है ना जो स्ट्रक्चर हमारे
as a particle trait.
क्योंकि अभी जब क्वांटम मैकेनिक्स होती है वहाँ पे पार्टिकल वेव ड्यूरेलिटी आपको नहीं पता कि वेदर ये वेव है ये हम इस वजह से ये सारा श्रोडिंगर इक्वेशन है वेव फंक्शन है कॉम्प्लेक्सिटी आ जाती है ये हम से फिजिक्स लेकिन टू बी वेरी क्लियर जो हीट है इट इज ए particle
quantum mechanically it behave like a particle. Yes. So now I will focus on the wave-wave interaction, and we have seen the wave-wave interaction for three waves, in which the pump wave is the incident wave on the medium. It has frequency omega naught and wave vector k naught. When it interacts with the medium, it scatters a sideband having frequency omega 1 and wave vector k1. The sideband has the comparable frequency of the pump. Now, beating of these two, the coupling of these two modes generates a low frequency perturbation, and the frequency of this perturbation is basically the difference of frequency of these two modes. So, having the frequency omega and wave vector k. So, this is nothing but the conservation of energy and momentum that is conserved. So, these are the two-phase matching condition which should be satisfied for the growth of the beat wave.
अगर इनमें से एक हो फिर
Which one, sir?
I mean कि अगर सिर्फ मोमेंटम कंजर्व है एनर्जी कंजर्व नहीं है तो हम तो कह सकते हैं
there is a possibility there is no if one conservation mode and another not.
Sir, if for example energy is not conserved, then it means that some energy is losing in the system in the form of heating or in the form of other forms. But it can be possible, but we are considering the system in which these two conditions are satisfied so that our beat wave will grow. We are interested in the growth of that beat wave. Now let me explain them.
एनर्जी और मोमेंटम क्या है अगर देखा जाए
Sir, एक ही चीज है basically.
आप एनर्जी स्क्वायर का डेरिवेटिव लो क्या मोमेंटम नहीं है
So let's examine the mechanism behind the parametric three-wave instability. As a first step, we inject a pump wave into the medium. When it interacts the medium, it generates a sideband having comparable frequency, and the beating of these two generates a beat wave, low frequency beat wave.
ये ना कि जो मैंने आपसे कहा था एक पंप वेव है दूसरी देखो किस वेव
Sir.
तो थर्ड वन है ना इट्स व्हाट
It's behaving like a heart.
उनकी इंटरेक्शन हुई है उनकी सुपरपोजिशन से ये चीज यहाँ पे
Definitely, sir.
that's मेथड क्वांटम
Right.
मैकेनिक्स में ये डील है ना वो भी हम साउंड में पढ़ते रहेंगे
Sir.
सुपरपोजिशन बट इट behaves or
Behaves like a particle.
ये particle है
Right. Now, the beating of pump and sideband generates a condramotive force which forces the particles towards the trough of the envelopes. The reason behind this is this force accelerates the particle in the non-uniform electric field of the beat wave towards the region of envelopes are basically ये जो this shape represents an envelope of a beat. That is the envelope. It's envelopes are basically envelope is envelope something. You are covering the boundaries of that region. Now, if this bunching of particle matches an electrostatic mode, then the three waves becomes resonant and the instability grows. Our mathematical model.
ऐसा भी हो सकता है कि रेजोनेंस वेव क्रिएट ही ना हो, जितनी मेहनत जो डैम्प होता है एक दूसरे को नलिफाई कर देता है. It's possible.
So it's possible, but it's like if there is a head-on collision, then these waves can destroy each other. Like that is something else. There is a possibility. Our mathematical modeling or quantum hydrodynamic model is based on following set of equations. The first one is the momentum balancing equation, which represents the dynamics of the particles in response to the three waves and under the influence of various forces acting on it in the medium. The second term on the left-hand side is the convective term. This is a nonlinear term.
Can you explain this term? Partial or partial T kya hai?
So this whole thing basically the derivative term, in which the first term is the time dependence derivative and the second term is the space dependence of the derivative. So this.
फर्स्ट टर्म है ना, ये अदर डिस्क्रिप्शन है. क्या चीज़ है? अदर डिस्क्रिप्शन. ई यू एल ई आर कहते हैं ऑर्डर. जो दूसरी है इसको हम बोलते हैं लैग्रेंजियन. लैग्रेंजियन का मतलब ये होता है कि हम किसी चीज़ को मूव कर रहे हैं उसके साथ और उसको ऑब्जर्व कर रहे हैं.
बिल्कुल.
और अदर का ये मतलब होता है कि मैं यहाँ पे बैठा हूँ या मैं
टाइम के साथ उसकी एवोल्यूशन.
अब कुदरत जनाबी जो पार्टिकल जो चीज़ आएगी ना, वहाँ से जब मैं ऑब्जर्व करता हूँ दैट इज कॉल्ड द ऑर्डर. जब हम इसको कंबाइन यहाँ पे करते हैं ना, दैट इज कॉल्ड एज द कन्वेक्टिव डेरिवेटिव. इसमें दोनों चीजें आ जाती हैं कि अगर मोशन है या ये कि यू आर स्टैग्नेंट ऑब्जेक्ट्स हैं, ये दोनों चीजें हैं. इसको हम कन्वेक्टिव डेरिवेटिव बोलते हैं. ये दो पॉसिबिलिटीज हैं. एक तो ये है कि आप एक पॉइंट ले लें, ठीक है ना, और उसको देखें कि वहाँ पे पार्टिकल कैसे जा रहे हैं, या ये है कि आप यूं करें कि पार्टिकल के साथ बात करना. जब आप मोशन में होंगे तो यू विल से इट इज लैग्रेंजियन डिस्क्रिप्शन. जब आप उसको फिक्स कर देंगे तो दैट इज कॉल्ड हैविंग ऑर्डरिंग डिस्क्रिप्शन. इसको जब आप कंबाइन कर देंगे दैट इज कॉल्ड
कन्वेक्टिव.
और ये जो अंडरस्टैंडिंग है ना, दैट्स वेरी वेरी इंपॉर्टेंट. हम इन मैथमेटिक्स लिखते हैं, टू लिखते हैं, हिस्ट्री लिखते हैं, क्या चीज़ हम डिस्क्राइब करना चाहते हैं. ठीक है,
राइट. On the left hand side, on the right hand side, we have the first term is the Lorentz force, which charged particle experienced in electric and magnetic fields. The rest of the three terms are the Fermi potential. This is the bomb potential terms. Sir, here the sir इसमें number densities involved हो रही हैं. और इसके साथ जो है उसकी हम चेंज देख रहे हैं सर पोटेंशियल्स की.
और
last term is the exchange correlation potential, sir.
Okay. Sorry, why you are put negative sign in exchange correlation? In some paper I have seen positive as well.
Sir, in some of the papers there is a positive sign, but the negative is hidden inside the potential term. They have incorporated the negative sign inside this potential term and written positive over here. So here I put it here, and the term that I will show later on for the potential is completely positive.
Actually, people just because it's a quantum term and nature of the particle, because bomb potential are positive, so people
use that
sign to it.
Yes.
Okay, but
basically it is with the negative terms.
Yes, sir. ये जो V है, VJ जो आपने सब्सट्रेट में लिखा है, VJ. What is this V? This is potential.
This is the exchange potential.
जो भी है तो potential.
Yes, sir.
बिल्कुल सही है. वजह ये है कि हमारे पास जो इलेक्ट्रिक फील्ड की डेफिनेशन है ना,
जी सर,
वो
नेगेटिव ऑफ ग्रेडियंट. नेगेटिव ग्रेडियंट.
अगर वो V में कहीं पॉजिटिव की है तो सॉरी, इट इज बेटर टू राइट इट इन दिस फॉर्म.
यस सर.
समझ है ना, क्योंकि
हमने यहाँ पर भी इसको भी जब आगे इसको करेंगे तो माइनस डेल्टा
लाजिम बात है.
जी सर.
हर टर्म की डायमेंशन सेम होनी चाहिए.
बिल्कुल सर.
ये क्या है? माइनस ग्रेड. अगर आप वहाँ पे पॉजिटिव लिखते ना, बिलीव मी, आई डोंट थिंक सो दैट इज राइट.
सर, दिस इज द करेक्ट वे टू राइट दैट ग्रेडियंट.
माइनस,
दैट्स व्हाट.
ये है कि इज इक्वल टू माइनस ग्रेडियंट.
जी बिल्कुल सर.
तो वैसे भी जो नेगेटिव पॉजिटिव साइन होता है वो पल्स से वो अट्रैक्टिव फोर्स.
हां
बिल्कुल.
लेकिन नहीं शहजाद, इलेक्ट्रिक फील्ड और ये इसकी पोटेंशियल को तो लाजिम बात है आप उसको ऐसे ही this is the standard definition. English ऊपर के नीचे है. Higher potential से lower
बाहर से लोअर की
potential.
तरफ आते हैं तो पोटेंशियल के साथ नेगेटिव ही होता है, उसका ग्रेडियंट नेगेटिव होता है.
Negative of the gradient is the electric field है.
बिल्कुल. So second is the equation of continuity, which ensures the conservation of particles in a unit volume. And the third equation that we have employed is the Poisson equation to calculate the electrostatic fields due to charge density gradients. And lastly, we employ the Maxwell-Curl equations to calculate the current densities due to the motion of particle in response to the electromagnetic sidebands.
Sorry, ये आपने serious में.
जी sir. Now, in the first problem that I'm going to present here, we have taken, sir.
Let's discuss. Look at partial E over partial B. What is this? Time rate of change of electric field. You are, mashallah, assistant professor at Superior University.
Sir, it is basically that.
Dimensionally, ये क्या चीज़ है?
So, dimensionally, it represents the change in the electric field.
बहुत नजर आ रहा है यार. Overall, जब ये change in electric field है तो क्या चीज़ produce होगी? देखो.
Sir, magnetic fields produce.
हाँ, बिल्कुल सही है. लेकिन the question is this कि ये जो है ना dE over dt, let me say, what is this? This is current density. और आपको पता है ये कहाँ प्रोड्यूस होती है? We call it as displacement current. और जब हमारे पास होता है ना कैपेसिटर में क्या होता है कि इलेक्ट्रिक फील्ड चेंज होती है जब हम उसको एसी देते हैं, ठीक है ना? तो इलेक्ट्रॉनिक करंट नहीं होती है, वो जो करंट आ रही होती है वो इस वजह से डिस्प्लेसमेंट करंट. और देखो कि अगर कोई आपसे पूछे कि ये पार्शियल ई और पार्शियल टी है, इसकी डायमेंशंस क्या हैं, तो लाजिम बात है हर टर्म की डायमेंशन सेम होती है. साथ वाली टर्म आपको ये है ऑब्वियसली समझ रहे हैं? हाँ, जैसे आप
basically two terms यहाँ पर हैं. एक तो आपका जो current density है due to the free charges and it is due to the bound charges.
एक जे है ना जो, हाँ बिल्कुल ऐसे ही है, बल्कि इसको ऐसे नहीं कहते बाउंड. एक होता है आपके पास कि जो आपके पास कंडक्शन इलेक्ट्रॉन.
सर वही फ्री हम कंडक्शन की सेंस में ले रहे हैं तो उसके लिए ये फर्स्ट टर्म होती है. सो सेकंड
एक जो है जब आपके पास करंट चार्जेस आर मूविंग
सर
ये करंट
बिल्कुल.
लेकिन कैपेसिटर के केस में जो होता है कि उस के इन बिटवीन प्लेट्स में स्प्रेड होता है डायरेक्ट चार्जेस को भी एक प्लेट से दूसरी प्लेट तक
नहीं जाता.
और ये जो है ना रेट ऑफ चेंज ऑफ इलेक्ट्रिक फील्ड दैट्स लीडिंग टू द करंट डेंसिटी. समझिए? हां. और ये इलेक्ट्रॉनिक करंट नहीं है, क्योंकि अगर हम उसको इलेक्ट्रॉनिक करंट तो सारी चीज़ तो बेटा होगा.
बिल्कुल.
इसका मतलब इंसुलेटर साउंड है, इलेक्ट्रॉन का कमी ऐसा नहीं है.
यस सर.
लेकिन इनकी जो है डायमेंशन वो सेम है. तो मेरा ये जो पॉइंट है जो आप बताना चाह रहा था वो ये है कि हर टर्म की डायमेंशन सेम होती है. कर ला पी लो कोई सी के साथ ये चीज़ है, ये भी जे है, सिमिलरली वो भी है, प्रोवाइड 4 5 है. ठीक है?
यस.
चलना.
The first problem that I am going to present here, we have taken the semiconductor dense plasma comprising of conducting electrons, and for this we have taken the upper hybrid wave as the pump wave.
Conducting electron as what? यही उसको डिफरेंशिएट.
जी बिल्कुल.
हाँ, यहाँ पे वो पार्शियल और पार्शियल टी की टर्म है
जी
वो इम्पोर्टेंट नहीं है. कंडक्शन नॉट स्लो करंट.
Yes. So we have taken the upper hybrid wave as the pump wave with frequency omega naught and wave vector k naught propagating in xz plane, making an angle theta naught with x-axis. It generates a sideband which we have taken as the electromagnetic O mode propagating parallel to the x-axis with wave vector k1. The two modes then couple together to produce an electrostatic electron acoustic wave propagating parallel to the external magnetic field along z-axis.
नॉट आपका बहुत दूर चला गया.
This one sir ये वो slide पे वो थोड़ा सा हो गया sir. So this geometry among the three modes ensures the phase matching condition among the waves.
Sir. आप पढ़ लो किसका मोड चूज करते हैं. How you choose this mode? That I am this mode will I am taking in my model, and they will interact and give me that result.
So basically, sir, ये मोड तो हमने एक चूज कर लिया, हाई फ्रीक्वेंसी वेव ले ली हमने अपर हाइब्रिड. Now these two modes should be chosen in such a way that this conservation of the vector conservation remains there. So ये आपकी O mode अगर ले रहे हैं, हमें पता है O mode जो है it is propagating parallel to the x-axis. Now if these two modes are there, then their result is basically k naught minus k1, which should be in this direction. This is basically a vector algebra, sir, behind.
आपने लेनी है बीट फ्रीक्वेंसीज.
Yes, sir. Sir, sir.
यहाँ तो मुझे उनके डिस्पर्शन रिलेशंस पता है.
Sir.
क्योंकि लीनियर तो आप निकाल सकते हो डिस्पर्शन
बिल्कुल
रिलेशन.
निकालेंगे सर.
नो इशू. यहाँ तो आप वहाँ से फेयर मैचिंग के ये फ्रीक्वेंसी इधर मैच करती हैं, तो मैं इनको इस कंडीशन में ले सकता हूँ. बीट फ्रीक्वेंसी जैसे आपने अपर ले लिया, लोअर ले लो, मैं लोअर चूज कर लूँ, तो क्या वो तभी मुझे रिजल्ट देगी?
सर लोअर, अगर आप लोअर हाइब्रिड ले रहे हैं तो फिर ये देखना पड़ेगा कि इन दोनों की कपलिंग से जो बीट वेव प्रोड्यूस हो रही है वो इस ज्योमेट्री को भी इंश्योर करे. सिर्फ एनर्जीज को इंश्योर नहीं हमने करना, हमने ज्योमेट्री भी इंश्योर करनी है अमंग द वेव वेक्टर्स.
ये कंफ्यूजिंग है आपका, ये आंसर कंफ्यूजिंग है.
ये जो ना सुपरपोजिशन ये जो कपलिंग टू मी,
ये आप चूज आपने मर्जी से नहीं कर सकते.
नहीं सर, इस तरह नहीं है कि रैंडमली हमने चूज कर लिया. डेफिनेटली वी हैव टेकन इन कंसिडरेशन देयर डिस्पर्शन रिलेशंस एज वेल एज देयर वेव वेक्टर्स, देन वी चूज द मोड्स.
Okay, this O mode is propagating parallel to the magnetic.
Yes, sir.
Perpendicular to the magnetic.
Perpendicular to the magnetic.
But O mode cannot propagate along the magnetic field.
So this is the geometry of O mode, that it propagates, the wave vector propagates perpendicular to the magnetic field, and its electric field vector is basically along the z-axis.
O mode is a simple electromagnetic mode, and it propagates parallel to the magnetic field or not.
So it's an electromagnetic mode.
It is electromagnetic.
Yes, sir.
And it cannot propagate parallel to the magnetic field. Always.
Yes, sir. It propagates perpendicular to the magnetic field, provided its electric field component is along the magnetic field.
ठीक है, सो क्या और
No.
certain constraints होते हैं.
Sir.
How the size and minor. So we have very very defined physics. But these are satisfactory.
That's it. So here is the summary what we are intended to do and how we do it. As a first step, we will do the linear response of the find the linear response of the medium to the three waves in considerations, and by employing the linearized equation of motion and the equation of continuity, we will find the perturbed linear velocity and number densities of the species in response to the three waves separately for the three waves, which leads to the calculation of linear dispersion relation of the three waves. Then, as a second step, we will do the field coupling among the pump and sideband, and due to this coupling, it generates the nonlinearity in the perturbation in the form of ponderomotive force. So calculation of ponderomotive force leads to the valuation of nonlinear velocity components, which when switched into the continuity equation will give us the nonlinear number density in response to the perturbation. And then we switch this nonlinear number density further into the Poisson equation to finally evaluate the electrostatic potential of the beat wave. As a second coupling scheme, we did the mode coupling of pump and perturbation, and the coupling of these two modes generates the nonlinearity in the sideband in the form of nonlinear current density. So by combining the two curl equations, we will arrive at this relation. And finally, we combine these two relations, these two coupling relations with each other. I will show you later that in the nonlinear current density, we will have the perturbed potentials. So we replace that potentials from the term that will derive from here. And by combining these two equations, we will arrive at the nonlinear dispersion relation of the beat wave. Now, lastly, for the evaluation of growth rate, we did Taylor expansion on the dielectric response function of the beat wave and the electric displacement of the sideband up to the first order. And by combining these two expansions, I will show you at resonance, we will arrive at the growth rate of the beat wave. So this is a bird eye view that what we are intended to do and how we will do it, which we'll do in the next few slides. So as a first step, we did the linear response of the three waves separately in consideration. First of all, with the pump, by employing the linearized equations, we will find the perturbed linear velocities components for the charged particles and the linear perturbed linear number density. And then we will, from this relation, we will move forward to calculate the electric susceptibility, linear electric susceptibility, and it leads to the evaluation of the linear dispersion relation by using this linear dielectric response function. So the quantities that are used in this relation are listed here. So this is the exchange potential, sir, where ABE is the bore radius, and this is our Fermi, the velocity term, incorporating the quantum effects, which are this is the Fermi velocity, this is the Bohm due to Bohm term, and this is the exchange, where exchange component is basically there.
Actually, the exchange correlation is a function of density.
Yes, sir.
It's a complicated.
It's a function, sir. It contains the equilibrium number densities of the.
No, but you have linearized it.
So this is the linearized.
This form is very simple, but in actual, it's a complicated density. What's a functional of density?
Yes, sir. So basically, we are finding the linear response, and for linear response, the equations. Sir.
But when it's a functional of density, then you apply some approximation. Then it becomes function of density. Have you used it?
So no, sir, we have just taken this relation. It is basically from the DFT theory that explain this thing. We are not expert in the DFT, but we have taken these relations from that.
But you have not applied any approximation
No,
for
sir.
this relation?
No, sir.
But people, they usually apply.
So they will apply. They have applied.
And you have used only electrons?
We are, our semiconductor, as I earlier said, it is comprising of conducting electrons, negatively doped and n-type semiconductors.
Ions or positive charge?
So we have considered the semiconductor which is negative charge doped because it comprising only of conducting electrons. It may have the, we have not, we are, so it may have holes due to impurities, due to minority holes it can have, but the dynamics is not affecting our mode. Because the modes that we are considering, electron are responding to them effectively.
What's the difference between mass difference between hole and electron?
So the effective mass of electron, as we have taken the example of gallium arsenide, it's 0.067 to the free mass of electron times the free mass of electron. But for hole, it is 0.5 times, I think 0.5 of the free mass of hole. For hole, it is different, greater. The mass is greater for hole.
What's the average difference? Like in electron and positron, we have ratio of 10 to the power
minus 3. We can divide these two values as I said, 0.067 to the 0.5, and we'll have the required number.
So you can ignore that holes.
So we ignore holes due to two things. First thing, we are considering a negatively charged doped semiconductor, which comprises of electrons. Holes, if they are there, then they are in the minority form. And the dynamics we can ignore. One thing, second thing, due to the high effective masses in comparison to effective masses of electrons.
Actually, my question is in semiconductor, can you ignore, is this your approximation practically valid or not? Because
Sir,
when there is holes in electrons.
Sir, if we are talking about the charge neutrality, then obviously holes, we have to take them. But we are dealing with the dynamics of electrons only in our case.
Why? Why? Why you are taking electrons?
Sir, I have already said, sir,
Low frequency or high frequency?
so we are considering the high frequency count wave. That's why we are ignoring the holes. The second linear analysis we have carried out on the sideband. So from linearized equation of motion, we have the velocity, perturbed velocity of the electrons for the sideband, and due to the geometry of the O mode, these perturbed velocity components in the x and y directions should be zero. So by combining the Maxwell equations, we have the usual linear dispersion relation for O mode.
No, just see. This linear dispersion of O mode,
So,
there is no magnetic field effect on electron. So it should be along the magnetic field, not in the perpendicular direction. Because if there is a perpendicular direction, then where is the gyro frequency of electron?
so gyro frequency appears from the term in the Lorentz force. It is B cross basically B. As I said that according to the geometry, the x and y components are zero. So the gyro frequency will not appear from that term because of the geometry. Due to the geometry, that's why previously I'm focusing on that the electric field is parallel to the magnetic field because that geometry will ensure the conservation. Now, lastly, we have done the linear analysis on the perturbation, that is electron acoustic wave. We again find the perturbed linear velocity components and the number density that leads to the linear electric susceptibility and the linear dispersion relation also. Here, by using this linear electric susceptibility, we use it later on to find the dielectric response function, which will be used in the evaluation of growth rate. We will use this relation later on.
Okay, let's just stop. Now there is a confusion term, and confusion in your this third calculation. You said it's an electron acoustic term. Okay. In plasma, electron to acoustic, they use when there are difference of temperature between two electron populations. Here you are getting electron Langmuir wave.
Yes.
Why you are calling electron acoustic? Then it will be confusing. You will confuse the reader because electron acoustic is used when there are two population electrons.
Sir.
This is electron Langmuir wave. Why you don't call it like electron? It's a Langmuir wave.
So it's the longitudinal waves along z-axis. That's why we have taken.
This is simple relation of electron.
Yes, sir. It is nothing but the electron.
Why you are confusing the reader? I also get confused. Where is the second electron? For using
Right,
electron
sir.
acoustic term.
So noted here. Sir. Noted here. We will. I will make.
Because there are some standard notation in plasma. Otherwise, you will confuse.
Noted, sir. So, as the first nonlinear response, for the nonlinear response, we did the first field coupling between pump and sideband that generates the countermotive force. This is the relation for the countermotive force that arises from the convective derivative term. And it generates, so after evaluating the pondromotive force, we will find the nonlinear velocity components, and then it will switch into the continuity equation to further evaluate the nonlinear number density. And then finally, for the evaluation of electrostatic potential, we use the Poisson equation. So this is the relation. It contains the E1Z over here, which is not showing here, sir. It is hiding from that. So as a second coupling scheme, we did the field coupling between the pump and perturbation that generates the nonlinearity in sideband in the form of nonlinear current density. This is the relation of the nonlinear current density. And by putting in the perturbed linear component that we have earlier derived in this relation, we will arrive at this relation of nonlinear current density. Then we combine the two Maxwell-Curl equations to have this relation, and we switch this nonlinear current density over here. And second switching that we do is the potential phi. We use this relation and switch it in this relation, and then further into this to finally arrive at the nonlinear dispersion relation of the beat wave, where mu is the coefficient of coupling, nonlinear coupling coefficient, and it's basically tells the strength of the coupling between the waves.
So now you have two phenomena of coupling.
So,
One is
mode coupling. One is between pump and sideband.
Sorry, one through
Pondromotive force. दूसरा सब it generates the due to non-linear current density.
और इस mu में दोनों का effect है.
दोनों का.
So which one is more stronger?
Sir, this is what we are going to analyze once we plot the growth rate curve. So to evaluate the growth rate, we treat the frequencies, daughter waves, that is the sideband and the perturbation as complex functions, and we did the Taylor expansion on the dielectric response function and the electric displacement up to the first order. Now here this imaginary part gamma is much smaller from its counter real part. So at resonance we treat the real terms as 0, and when we multiply these two equations we arrive at this relation. Now we compare this relation with the previously derived relation for the nonlinear dispersion relation, and by comparing two we arrive at this formula. These differentials we evaluated separately, and the terms for these differentials are over here. And then by switching in all the ingredients, we have the final recipe for the growth rate of the beat wave as here. Now, to appreciate the numerical results, we do some graphical plotting, and these are the standard values that we have taken for the medium that has been quoted by several researchers. I have mentioned here two of the papers.
Which type of semiconductor?
So we have taken the example of gallium arsenide. This graph is between the dielectric response function. It is the graph between electric susceptibility and the pump wave frequency, incident pump wave frequency. This graph tells the strength of polarization that is produced in the medium to the incident pump wave field. And it is shown here that the medium shows a greater response in terms of polarization for relatively lesser values of the pump. And this response gets weaker as we increase the pump wave frequency. So this is basically the response of the medium, and from this we will find out that which kind of pump frequency is suitable for this medium. So as we earlier said, sir, why you choose this? Because of the response of the medium that is shown over here.
So you need more response, or whether you need?
We need definitely more response. Why? Because this response contributes to the growth rate.
Okay.
We are interested in the growth rate of the instability.
Okay, so as you go to less frequency of
Relatively lesser values of the frequency, we get the greater response. And this,
how you will decide in the
sir, one thing is from this graph. From this graph, we see I cannot choose this value.
Okay, just if you go to 10 power 12, then response will be higher or not?
No, sir. In the previous regions, we see that the medium is not showing any response over there. So we are getting the response in this region.
क्रिटिकल पॉइंट लिया जहाँ पे रिस्पांस शो किया
Sir?
बेटा वो क्रिटिकल पॉइंट आपने लिया
कौन सी वो critical point?
फ्रीक्वेंसी जहाँ पे आपका ये जो है रिस्पांस आना शुरू हुआ डू यू नो हैव यू कैलकुलेटेड
No, sir, we are not
interested
no, sir, not interested. It means that we have not do this analysis, but we have selected a range of frequencies, and in this range we explore which one is more suitable for this medium. We are basically comparing between the frequencies.
Yeah, just for physics, it's not a complete information. You have to find first define your range. In that range it lies, whichever you say that in that range it lies.
Right.
Then you can say that in that response it is showing this behavior, and I will choose this one. Otherwise you can't say. You go 10 power 12, 10 power 11, you can also go there.
Okay.
Now,
ये सारा प्रोसीजर आपने किया हुआ है
जी सर।
किया हुआ है सब you have to sit and play with it.
Yes, sir.
Nice.
Yes,
That's
sir.
okay.
This is the graph this is the graph of normalized growth rate of the beat wave for 3 different values of the pump frequencies or K0. And 2 things are explained in these graphs. That one thing is for higher K values of the pump or higher frequencies of the pump, the rate of growth shows a decrease. And as we move towards lower values of K0, that is the lower frequencies of the pump, the rate of growth increases. This is basically the continuation of previous concept that we have seen in the graph, that relatively lower frequencies are showing greater towards the electric susceptibility, and same response is showing in the terms of growth rate of the beat wave too. The second thing that we observe that for lesser K values, we see the growth rate increases in all the 3 graphs and up to a threshold value, after which a decrease is observed. This is basically due to the phase matching condition, that at this particular point, the phase matching, the modes are showing the phase matching condition is fully satisfied, and after that a phase mismatch is observed, which keeps on decreasing as we keep on increasing the K. This can also be seen from the K1, the value of K0 and the K value. If I take any value that is theta naught, I have, for example, I take it 15 and K0 is to 10, and K1 will be evaluated for from any of the here value. For example, if I take 50, then K1 should be satisfied, and this equation is basically from the phase matching condition that I have earlier shown.
Okay, just stop. One point. This omega is which frequency?
So this is the real part of the frequency of the, this is the perturbed wave frequency.
What means?
Perturbation, sir. The electron acoustic that I have said. Laminar wave. Yes, sir.
The ratio of instability gamma by omega or
Omega.
wave.
Yes.
This ratio is very low.
Very low, sir.
Why?
So we can plot it by simply with omega as we have done. Sir. Sir, because this I have said that this real imaginary part shows the growth and it is very less than its real counterpart.
It should be.
It should be lesser.
This is correct. But 10 to the power minus 16, you can't observe. It's very, you have to be very precise in your instruments.
Yes, sir.
You can
Sir, for experimental observation, definitely it's very, but for our graphical plots, we have taken it like
But
this.
you can check. I don't know. You can check. It should be of the order from 0.1 to 0.00 of that order 10 to the power minus 3. It should be in real. Or maybe you are doing dense plasma, so it may be shift
Yes, sir.
in more
Parameters, three parameters.
or maybe
So
because in quantum scale you need to be more precise in your observations. Then maybe just check again
Right.
you confirm your parameter. If it is coming in that range, I don't say that it will be wrong if you are getting it, but just check it.
Right. Right. The next graph is the graph of normalized growth rate of the beat wave for different incident angle of the pumps. Theta naught is the angle between the pump and side band. So the thing that we observed from here that by increasing the angle theta, we the coupling between the pump and side band shows more coupling, the strong coupling, because it leads to the increase in the growth rate. So it means the modes are coupling strongly, that's why the growth rate is increasing. The second response is again same, that for lower k values, the modes are matching towards the phase matching condition. That's why we observe an increase and decrease due to the mode mismatch. But the thing that is here, that the threshold values are now shifting to higher k values. This is due to the mode matching, as it is shown here. It can also be verified from this numerical result, that as I increase theta naught, the cos theta naught decreases, and the term that is subtracting from the main term gives you the overall effect is k is increasing basically. So that's why k is shifting to the higher k values. This is the graph between of the normalized growth rate of the beat wave versus the external magnetic field for three different equilibrium number densities of electron. What we observe in here, that as we increase the external magnetic field, the rate of growth, the normalized rate of growth decreases. The reason behind is that by increasing magnetic field, the gyro frequency of the electrons are increasing, and we observe a mismatch in the resonance between them. It can be also seen from our numerical results here. Sir.
Not the value here.
Sir.
Or वो आप उधर show करा के fix
Sir, sir.
तो बड़ी less है ये ज़्यादा है
10 to the power 4 to 10 to the power 6 की रेंज में हम ले रहे हैं.
तो आपने जो ग्राफ दिखाया था वो
तो ये 10 to the power 5, यहाँ से 5 से लेके हमने 6 की रेंज में. जी सर.
ये देखो डिटेल्स को 4 है.
Sir, it can be checked for other values also. Same response will be there, but obviously shifted to some other values. The response is same. हमने सिर्फ एक ग्राफ प्लॉट किया, हम इसको डिफरेंट और भी प्लॉट कर सकते थे, but I have shown only here. So this response is due to the lack in resonance between the waves. And second thing is by increasing the number density. By increasing the number densities, we observe that the rate of growth decreases. So it represents that a heavily doped semiconductor shows a decrease in the growth rate of the peak wave. From all these numerical and graphical results, we come to the conclusion that semiconductor dense plasma shows higher susceptibility and also an increase in the growth rate for relatively low incident pump frequencies, whereas these response get weaker for higher values of the pump frequencies. The mode coupling between pump and sideband is strongly dependent on the orientation of the incident pump wave and shows a higher growth rate for larger angles between the two modes. The low frequency beat wave shows a weaker response to the high value of external magnetic field due to the high gyro frequency of the electrons and hence reduction in the growth rate. And lastly, the growth rate of the perturbation decreases with increase in the electron equilibrium number density. It reflects that a heavily doped semiconductor shows the decrease in the growth rate. Now I will move to the second problem. This is in mechanism, we can say this is the same as the previous one, but the only difference here is the dense plasma environment, which is now case is the astrophysical dense plasma comprising of electrons, positively charged ions and dust particles of negatively charged. And the difference is also there for the modes that we are now going to explore in the dense plasma environment. The geometry of the three modes that we have considered is the interaction is over here. Here, dust ion acoustic wave is taken as the incident pump wave propagating at wave vector k naught parallel to the external magnetic field. It generates a electromagnetic sideband, which is shear Elman wave, propagating at wave vector k1, making a small angle theta1 with the external magnetic field. The coupling of these two modes generates a low frequency electrostatic dust lower hybrid wave, and it is propagating with wave vector k, making an angle theta with the x-axis. The important thing about this geometry is the dependence of this is theta1, sine theta1. If I can move this upward slightly. Sir, ये move नहीं हो रहा, वरना मैं इसको हो गया sir. So the important aspect of this geometry is the dependence of the perturbed angle theta on the theta1. So by only controlling the sideband angle, we can find the dependence on the beat wave geometry.
Okay, so just stop. What is this SAW?
Shear Elman waves.
Okay, you are taking two more dust ion acoustic, dust low hybrid waves.
So
These both are electrostatic.
these both are electrostatic.
Then you are generating
Electromagnetic shear Elman waves.
it is dust shear Elman wave or
It's a simple shear Elman waves.
then there, I'm just saying you are taking dust in two more.
So it is basically so we have seen shear Elman wave, but obviously in medium wise dust is also there and their contribution should also be reflected over it. So it is basically dust shear Elman wave. We can say like this. Now we proceed with the same procedure. First, we find the linear response of the pump, the sideband, and the perturbation in the same way as we previously did, and find the dispersion relation for pump wave, omega naught, and the shear Elman wave, dust shear Elman wave, omega 1 over here. And for perturbation, we arrive at the susceptibility value which we use for the in the dielectric response function later on. For nonlinear response, the same coupling mechanism between the modes, first between pump and sideband, that generates nonlinearity in perturbation to find the electrostatic. Yes, sir. This is the sir. Sir.
ये आपका वर्क पब्लिश हुआ?
Yes, sir. Both works are published, sir. So this is the, sir, final relation of the growth rate of the beat wave. And now for the graphical analysis, we have taken the example of these are the values which many researchers have quoted in their papers for the dusty astrophysical dense plasmas. And these are the parameters.
So just you are saying dusty astrophysical plasma. Which
Sir.
type of compact star are you?
Sir, we have taken the example of a neutron star. Sorry, void walk, sir.
Void.
And for these, we have. So this is the graph.
ये जो बचे पैरामीटर्स आपने सारे लिए हैं,
Sir.
प्रैक्टिकल है या किसी एक्सपेरिमेंटल ऑब्जर्वेशन है?
Sir, these are the experimental observations which are quoted by several researchers in their theoretical works. They have, I have shown one of them, sir. I have shown one of them, but they further referred to so many, in literature we find so many other references.
इसलिए कह रहा हूँ डॉक्टर साहब,
Yes, sir. Yes,
मैं
sir.
अभी ये अंडरस्टैंड कभी कभार ना इस तरह की एग्जाम लगा लेता हूँ।
We understand,
क्या
sir.
चाहिए उसको रीड टू बी, तो मैं ये कह रहा हूँ कि आप बड़ी मेहरबानी करके ये डाटा मुझे दे दीजिए। ताकि मैं ये कह सकूँ कि बड़ा स्टैंडर्ड है ये मेरा वर्क।
Okay.
So as the first graphical response, we see the growth rate of the beat wave versus the sideband angle θ1 for three different external magnetic fields.
Okay, आप
Just now you see. Why in your y-axis you have not plotted gamma or?
So that's why I earlier said that we have just taken it like this, but we can also plot it with the normal growth rate
If
too.
you are plotted in one sense,
Sir.
then other plot should be the same. Then you can think your thesis will be good. Otherwise, there is complication. Because I don't
Right.
know where is what was it.
तो मैं बता रहा हूँ सर, मैं बता रहा हूँ।
So try to plot the same.
Right.
You have gamma over gamma. Then
लेकिन अगर ऐसी बात है जो सजा डायरेक्ट सुनी, लेकिन पास में ये भी होता है कि आप एक चीज है वो डोमिनेंट नहीं है, उसका फैक्ट आप देखना नहीं चाह रहे, उस पर बस बताओ उसको दे सकते हैं और बस इसका अप्रॉक्सीमेटली
एक चीज नाम
नहीं, आपकी बात
ठीक
ठीक
है,
है।
लेकिन एक चीज मतलब gamma को जब आप फिजिकली देख रहे होते हैं, आपको पीछे रियल फ्रीक्वेंसी की वैल्यू चाहिए होती है, वरना तो आप बता नहीं सकते वो सही है या
बिल्कुल, dispersion relation से यही है।
प्लॉट आपका सही था,
जी सर।
gamma और gamma, मैं दूसरा कुछ ही ना करूँ ना,
Right.
उसको बदलो ना, यहाँ तो मैं बताओगे मैं क्या कह रहा
हाँ ये क्या बताओ
हूँ, अगर फिजिक्स देखनी है तो नहीं आप पता चलेगा कि अब ये फिजिकल भी है कि नहीं, वो तो वहीं से मुझे पता चलेगा gamma और gamma वो मेगा रेशियो।
ये डिफरेंस का ही मतलब होता है ना यार,
सर ठीक है।
क्या आपने ये किया, क्यों किया, किस लिए किया?
बिल्कुल सर, बिल्कुल सर। So here we see that by increasing θ1, which is the angle between the pump and sideband, we see a decrease in the growth rate. So it's mean the pump and sideband with lesser inclination between them shows a more strong coupling. So strong coupling and hence the growth in the growth rate. Second thing that we observe here, by increasing the magnetic field, the growth rate is now increasing. So this represents that by increasing magnetic field, the gyrofrequency of the electrons are increasing, and hence it contributes to the frequency of the beat wave.
ये ग्राफ मैथमेटिकल प्लॉट
Sir, mathematical plots, yes.
मैथमेटिका में
Mathematica, sir, yes, Mathematica.
अच्छा तो आप वैसे जनरल आप क्या चाहते हैं इसमें कि ग्रोथ रेट ज्यादा होना चाहिए आपके लिए?
सर हम ऑब्जर्व कर रहे हैं कि आपकी इंस्टेबिलिटी अगर ग्रो कर रही है तो ग्रोथ रेट उसका फिर ज्यादा होना चाहिए, और हम वी आर इंटरेस्टेड इन कि हमें ग्रोथ मैक्सिमम कहाँ मिल रही है, एट विच
बेसिकली आपका प्रॉब्लम इंटरेस्ट है कि जहाँ पे मुझे मैक्सिमम मिले,
मैक्सिमम ग्रोथ
नीचे वाले में
रेट।
नहीं इंटरेस्ट आपका जहाँ पे
सर डेफिनेटली वहाँ पर भी कुछ फिनोमिना होंगे जो हमें वहाँ से भी इंफॉर्मेशन देंगे अबाउट द मीडियम, बट वी आर फोकसिंग दैट हाउ द इंस्टेबिलिटी इज ग्रोइंग ड्यू टू दिस इज पैरामीट्रिक इंस्टेबिलिटी।
मैं ये करूँ कि आप कौन से रीजन में इंटरेस्ट हैं, ग्रो वाले में?
We are interested in the growth of the
कई होता है जैसे वो कहते हैं कि हमें डिके वाले रीजन में।
नहीं सर, हम ग्रोथ की तरफ ज़्यादा हमारा फोकस है कि ग्रोथ जो है आपकी,
जो है पंप जो है
जो बीट वेव प्रोड्यूस हो रही है उसकी ग्रोथ कैसे हो रही है इन द मीडियम. This is the graph of growth rate of the beat wave versus magnetic field. The same response is shown here that by increasing magnetic field, the growth rate increases. But now with the three different number densities of the electrons, equilibrium number density. And we see that by increasing the equilibrium number density, the rate of growth decreases. This is the reason behind it, that decrease in the equilibrium number density of electron means the more charge is gained by the dust. And the dust dynamics now becoming important, which contributes in the growth rate. This is the graph between the rate of growth versus the equilibrium number density. The same behavior, that by increasing number density, growth rate decreases, but now for the three different values of the pump frequencies that are injected in the system. So here we see that if more energy is injected in the plasma, then more growth is observed of the beat wave. To conclude, the parametric growth rate of the beat wave shows an increase with the increase in the incident pump energy. Electromagnetic shear Kelvin wave shows an increase in the growth rate for small inclination angles with the pump wave. For larger angle, the coupling becomes weak. An increase in the external magnetic field shows an increase in the growth rate that shows that the gyro frequency of the plasma species is highly coupled in phase with the oscillating beat frequency for the large value of external magnetic fields. Increase in dust charge enhances the dusty plasma dynamics, contributing the growth of the perturbation, that is dust lower hybrid wave. Thus, growth rate of the beat wave highest for lesser values of equilibrium number density of the electrons. So this is it, sir. So these are the list of publications that we have done.
So thank you, Zahid. Now house is open for the audience. You can ask any questions. Zahid, please come on. You have to stay at here. Yeah, okay. So please, house is open now.
Dr. Jamil, can you show the publication list again?
Yeah.
Sir. सर वो कैट दिखाएंगे.
Question. House is open, please.
Okay. If anyone want to ask, please ask the questions.
Sir, are you going to ask a question, sir?
No, please ask the participants to get done.
Yeah, yes, that's
So
the
we
reason
have-
it's announced. No question is coming.
सर मैं जवाब.
Basically, what happens कि आप K को increase कर रहे हैं और growth rate आपकी hump जो है वो decrease करनी शुरू कर दी. एक time आया तो वो increase की.
सर
Maximum हुई.
बिल्कुल.
तो क्या हुआ कि फिर वो decrease करना शुरू.
सर ये ग्रोथ रेट जो है द पैरामीट्रिक इंस्टेबिलिटी इट शोज दैट कि आपकी मोड्स जो हैं फेज मैचिंग कंडीशंस को सेटिस्फाई करें. सो अगर मैं यहाँ से k की लेसर वैल्यूज ले रहा हूँ, बिकॉज एज यू कैन सी ऑन द ग्राफ k नॉट आई हैव ऑलरेडी चोजन. k नॉट इज 200 per centimeter and k should be satisfied from this condition. सो होता क्या है कि जब आप लोअर के वैल्यूज की तरफ होते हैं तो वो के वैल्यूज जो होती हैं वो जैसे जैसे आप इंक्रीज करते हैं तो आप फेज मैचिंग कंडीशन की तरफ अप्रोच कर रहे हैं. जो मैक्सिमम है it represents that the phase matching condition is totally satisfied among the three modes. और उसके बाद डिक्रीज इसलिए होता है कि आपकी मिसमैच इन द फेज हो रहा होता है बिटवीन द मोड्स, तो ये इस वजह से आपका ग्रोथ रेट डिक्रीज कर रहा होता है. So our growth rate is very much dependent on the orientations between the three modes. सर हम थीटा सर थीटा 0 और 90 के दरमियान हम कोई वैल्यूज को चूज कर सकते हैं क्योंकि ये अपर हाइब्रिड वेव है. सो लो इफ वी आर मूविंग टुवर्ड्स द लोअर वैल्यूज ऑफ थीटा इट्स मीन वी आर मोर इंक्लाइंड टुवर्ड्स द साइक्लोट्रॉन फ्रीक्वेंसीज, and if we are moving towards higher values of theta then we are more inclined towards the oscillation frequencies, plasma oscillation frequencies. सर अगर आप थीटा डिक्रीज करते जाएंगे आपका ग्रोथ रेट डिक्रीज होता जाएगा. सर मैं वो बता रहा हूँ कि वो 0 और 90 के दरमियान हम कोई वैल्यू चूज कर सकते हैं. तो ये है सर हमने इन 3 वैल्यूज के लिए चूज करके देखा है. इसके अलावा भी आप कोई भी वैल्यू ले सकते हैं उसके दरमियान.
One question, although you have done a good work, the presentation was very nice. Just one question on your topic. When you have studied this parametric decay instability, you say, is it
parametric instability?
General plasma literature. People also studied modulational instability in this study. Why you miss this modulational instability? Because you have shown the modulated wave through beat frequency, the amplitude. People also expected.
Sir, modulation frequencies, amplitude modulations basically उसमें वो होती हैं. हम जी सर. Sir, we have focused on the only on the modulation of frequencies. That's why we can focus on the other one.
Sir, I'm just asking why you missed this modulational instability calculation. And other question is, now you have you got this sideband frequency which you said. What will happen to the system? Is it in which sense it is useful for your system, or it is bad for your system?
Sir, इसकी जो applications है, it is in the प्लाज्मास एज वेल. इसकी जो ज़्यादा जो है अगर एक्सपेरिमेंटल उस पर जाके देखें तो टेलीकम्युनिकेशन के अंदर भी ये फिनोमिना यूज़ हम कर रहे होते हैं. मोड कपलिंग के आपकी जो पैरामीट्रिक ऑसिलेटर्स हैं वहाँ पर भी हम इस फिनोमिना को अप्लाई करके वहाँ पर भी देख सकते होते हैं कि मोड कपलिंग किस तरह से वहाँ पर, क्योंकि नॉइजेज जो जनरेट होती हैं इन द सिग्नल या अब जो हाई फ्रीक्वेंसी स्विचेस यूज़ हो रहे हैं.
मैं आपके एप्लीकेशन पे
सर
मुझे दूसरे नहीं चाहिए. सर आपने स्टडी के सेमीकंडक्टर इलेक्ट्रॉन लाइन में कर दिया.
सर
उससे सेमीकंडक्टर की मैन्युफैक्चरिंग में क्या असर हुआ या जो भी आपने स्टडी की?
सर हम उसके अंदर जो सेमीकंडक्टर के अंदर अब जो वेव्स प्रोपोगेट आप करवा रहे हैं, आप ये देखना चाह रहे हैं कि वहाँ पर जब ये वेव्स आप प्रोपोगेट करेंगे और आपस में इनकी जब इंटरेक्शन होगी और वहाँ पर नॉन लीनियर इंटरेक्शन से कोई पैरामीट्रिक इंस्टेबिलिटी जनरेट होगी तो वहाँ पर इन दैट इलेक्ट्रॉनिक डिवाइस वो क्या रोल प्ले कर रही होंगी. लाइक नॉइस, दे जनरेट नॉइस प्रोड्यूस कर सकती हैं. आप उस नॉइस को अगर स्टडी करना चाह रहे हैं तो दिस वर्क इज वेरी यूजफुल. डेफिनेटली वो यहाँ सर देखिए ना, नॉइज प्रोड्यूस हो रही है, इट्स मीन इट इज प्रोड्यूसिंग ड्यू टू द ग्रोथ ऑफ द इंस्टेबिलिटी. सो हमने उसको कैसे अब कंट्रोल करना है. सर हमने एक तरीका बता दिया कि इस तरीके से नॉइज प्रोड्यूस हो सकती है. नाउ इट इज द टास्क ऑफ द इंजीनियर्स टू हाउ टू हैंडल दैट नॉइज. सो दिस इज व्हाट वी हैव डन. जी वाली जी सर. सर हमारा जो मीडियम हमने लिया है हम वो ये रिफ्लेक्ट कर रहा है कि फॉर अगर हम उसकी डॉपिंग हैवी कर रहे हैं तो ग्रोथ रेट जो आपका प्रोड्यूस हो रहा है इन दैट लो फ्रीक्वेंसी बीट वेव दैट इज डिक्रीजिंग। तो हमारा जो मीडियम है हेवीली डॉप मीडियम, वो ग्रोथ रेट को यूँ कह लें कि ग्रो नहीं करने दे रहा है, उसकी ग्रोथ नहीं हो पा रही है हेवीली डॉप में। और अगर आप डॉपिंग कम करेंगे तो वो ग्रोथ रेट ज़्यादा कंट्रीब्यूट करेगा। तो ये मीडियम का रिस्पॉन्स है एक तरह से दिखाया जा रहा है।
एक चीज, ये जो गामा और ओमेगा है
सर,
ये आपका नॉर्मलाइज्ड है
सर नॉर्मलाइज्ड हमने ग्रोथ रेट,
तो इट मींस कि आप नॉर्मलाइज्ड को अननॉर्मलाइज्ड के साथ plot
सर
तो अगर आप अपनी सारी इक्वेशन को भी नॉर्मलाइज
सर यही सर ने अभी कहा था कि अगर आप इसको वैसे ही हम ले लेते हैं जैसे जनरल गैमा हम अगली में ले रहे हैं, तो फिर इट्स ए गुड सजेशन सर, नो डाउट वी कैन नॉर्मलाइज द होल इक्वेशन। ये है कि नॉर्मलाइज करते हुए वो ये ना ऐसे पैरामीटर्स इन्वॉल्व कर रहे हैं जो खुद वेरी कर रहे हैं। इट हैपेंस सर, यस सर, क्योंकि हमने उन पैरामीटर्स के साथ नॉर्मलाइज करना है जो फिर उनकी वेरिएशन ना आगे देख रहे हैं।
लेकिन
सर
दिक्कत यही है कि आप नॉर्मलाइज अगर एक करें ना
तो फिर पूरा भी हो। जी सर,
लेकिन मैं फिजिक्स है ना, इट रिमेंस
इंटैक्ट, इट रिमेंस इंटैक्ट।
वैसा मसला नहीं है क्योंकि हमारे पास ऐसी चीजें होती हैं, हम मसलन यूनिट एक चीज है, हम उसको यूनिट से नॉर्मलाइज कर रहे हैं या बिल्कुल दैट्स नॉट ए प्रॉब्लम। मसलन b ओवर t नॉट है,
जी सर,
t नॉट को 1 ले रहा हूं और मैं b को वैसे ही ले रहा हूं, क्या फर्क पड़ेगा? ये और इट्स ओके, फिजिक्स समझ आ जाती है।
So is there any more question? So if there is no question, we pay thanks to the audience, and I request to the audience, please give us a few minutes. Thank you. The external examiner would stay, and audience are requested to give few minutes to decide. Sir, ऑडियंस बाकी चले गए हैं, अब आप आगे प्रोसीड करें प्लीज सर।
ठीक है, क्वेश्चन है सच, इनका सिनॉप्सिस कब अप्रूव हुआ था?
सिनॉप्सिस कब अप्रूव हुआ सर? सर वो लिखा तो है पीसीडीसी है
16 है
नहीं 15 या 16 कह रहे हैं सर, अभी पीसीडी पे लिखा है लेकिन इसमें यार
क्योंकि 19 में इनका आखिरी पेपर है ना, उसके बाद कोई ऐसा पेपर नज़र नहीं आया इनकी लिस्ट में, तो वो सिनॉप्सिस के बाद इनके पेपर्स हैं, फिर तो कोई ऐसा इशू नहीं
सर, बात के ये सारे ये
सर, ये मैं आपको दिखा दूं।
ठीक है
है जो आपको पहले का नजर आ रहा होगा।
हाँ, सिनॉप्सिस से पहले का एक पेपर है, एक वन पेपर,
ठीक,
दिस नंबर 2014 वाला सर।
यस,
बाकी सारे जो है वो आफ्टर दैट है
सर। मेरा तो ऐसा स्टूडेंट्स और कोई क्वेश्चन नहीं है।
नहीं सर, चले गए सब लोग, बाकी अब सिर्फ एक्सटर्नल्स और हम मौजूद हैं।
ठीक है, स्टूडेंट भी इधर ही हैं।
यस सर, स्टूडेंट को भेज दें, आप भी चलें।
हाँ जी, मेरे ख्याल में अगर और कोई क्वेश्चन नहीं है टेक्निकल,
यस सर, आप बाहर वेट करें प्लीज। सर आप सर रिस्पेक्टेड प्रोफेसर से
और डॉक्टर मोहम्मद इकबाल, थैंक यू वेरी मच, यू हैव स्पेयर टाइम टू
आपका थैंक्स कर रहे हैं। अस्सलाम वालेकुम।
वालेकुम सलाम।
क्या हाल है सर, ठीक ठाक हैं आप? पहचान लिया कि नहीं? भूल गए?
ठीक ठाक हैं।
हाँ यार, सब ठीक। अच्छा यार, सही है सब कुछ। हाँ माशाल्लाह, अब आपकी शक्ल नजर आ गई। वो मुबारक हो यार आपको चेयरमैनशिप।
चले खैर, मुबारक जनाब।
इंशाल्लाह मुलाकात जब आऊंगा ना तो मुलाकात करें,
किसी वक्त आए जनाब, मुलाकात करेंगे।
पहले मैडम के साथ तो चलता रहता था, वो आजकल रुका, मैडम तो चली गई ना, तो बड़ा पेपर हमने सबमिट किया, देखते हैं अब इंशाल्लाह।
ठीक है, तो बाकी आप सेटिस्फाइड हैं इनके थीसिस से, प्रेजेंटेशन से?
हाँ, थीसिस में मैं थोड़ा सा बताऊंगा इनको, वो थोड़ी चेंजेस चाहिए तो वो इनको बता दूंगा, जो थोड़ी मिस्टेक्स हैं वगैरह ना। प्रेजेंटेशन अच्छी थी इसकी ना, और
मतलब कोई काफ़ी चेंजेस हैं या कोई माइनर सी चेंजेस उसमें हैं?
माइनर ही हैं,
ठीक है। और प्रोफेसर इकबाल साहब,
अस्सलाम वालेकुम सर।
वालेकुम सलाम।
कैसे हैं आप?
खैरियत से हैं?
वेरी नाइस, अल्हम्दुलिल्लाह बिल आलमीन। यार
बहुत
हैप्पी
शुक्रिया जनाब, आपने टाइम निकाला
बच्चे, वेरी नाइस।
तो इनकी प्रेजेंटेशन और तीसरे से आप सेटिस्फाइड हैं? ये कमेंट्स आपके?
बहुत अच्छी प्रेजेंटेशन है इसकी और
ठीक है,
बड़ा अच्छा काम है। हाँ
ठीक हो गया।
बहुत
तो
अच्छा
आप
है, वेरी नाइस।
अप्रूव कर रहे हैं फिर इनको?
बिल्कुल मैं अप्रूव कर रहा हूँ, बिल्कुल ही डिजर्व्स डिग्री। आप उस पर अवार्ड करें और अल्लाह ताला आप सब लोगों को खुश रखे। दैट्स वेरी गुड एक्टिविटी। और ये
ठीक,
थ्योरेटिकल अंडरस्टैंडिंग और काम करना इट्स नॉट सो इजी, लेकिन मैंने देखा है कि बच्चा जो है ना माशाल्लाह ही हैज डन अ लॉट, वेरी नाइस।
ठीक है, ठीक हो
ही
गया जनाब,
डिजर्व्स।
ज़बरदस्त ना। तो
हाँ
बस मतलब अगर आप अप्रूव कर रहे हैं तो फिर बाकी तो वो जो परफॉर्म है ज़ाहिर बात उस पर एक्सेप्टेड और वो लिखना होगा कि अगर कोई चेंजेस नहीं है सच
नो
आपकी तरफ
इट्स
से।
ओके, इट्स फाइन,
अच्छा,
अल्हम्दुलिल्लाह दे
ठीक,
हैव पब्लिश्ड वर्क। हाँ इट्स ओके। हाँ
ठीक हो गया।
बिल्कुल
तो
सही,
बस वो आपके सिग्नेचर वगैरह आपसे करवा लेंगे।
ठीक है।
तो थैंक यू अगेन। और
Okay, thank
स्टूडेंट
you
को
so
मेरे
much,
ख्याल में
sir. You
हाँ जी,
invited us. May Allah subhanahu wa ta'ala bless all of you. Okay. And wishing you all the best in your future endeavors.
थैंक यू।
Okay, Allah Hafiz, sir. Okay, thank you, Allah Hafiz.
Sir, shall I announce to successful defense and
बिल्कुल
closing
ना,
this?
सक्सेसफुल डिफेंस
Yes.
अनाउंस कीजिए। आपको भी बहुत मुबारक हो और
Thank
स्टूडेंट को
you,
भी
sir.
मुबारक हो
Thank
जनाब।
you. So this defense is declared as successful. Alhamdulillah. Alhamdulillah. Thank you,
कंग्रेचुलेशन
sir,
टू ऑल।
for your kind supervision and efforts. Yeah, मैं student को बुला के
हाँ,
हाँ।
स्टूडेंट को बुला लेंगे।
आपको बहुत बहुत मुबारक, वेरी नाइस, गुड कंट्रीब्यूशन रियली माशाल्लाह। 2014 से बच्चा रिसर्च कर रहा है यार, इसका एमफिल किधर है?
So Zahid Mir is here, sir. You can
जाहिद
congratulate.
मीर,
Sir,
कंग्रेचुलेशन।
thank you, sir.
Now you are Dr. Zahid Mir. Congratulations
Thank you,
to
sir.
you and to your supervisor and all your team. All the best.
Thank you, sir.
Thank you,
so
sir.
much, sir.
Thank you. Assalamu alaikum. Allah Hafiz. Allah Hafiz.
वालेकुम अल्लाह हाफिज़, अल्लाह हाफिज़, थैंक यू।
जरा मुझे मिले जरा डॉक्टर साहब, डॉक्टर साहब मैं मरीज हूं, जरा मुझे सही तरीके से मिले ताकि मुझे अल्लाह ताला से बहुत बहुत मुबारक हो।
टीम साहब तो हमने देखे नहीं कि मेल में है इसे है
खैर जो अभी
एक मिनट
और
हैं
को हो गया ना थोड़ा
उनका फिर नाम नहीं है, थोड़ी जबरदस्त है वो पेज
ये हम उसके सामने
थैंक यू। आप बहुत ऑनर है, आप इस ऐसे शहरों में हमारी
अंदर आ